Welcome back to the Subspace Mechanics channel. Today we're going to review basic quasi-fluid formulation of subspace mechanics, in which we assume that the constituents of our subspace are gyrons, which have a position in subspace, a velocity in subspace, and an angular momentum in subspace at a given time t. Now this quasi-fluid formulation is of course not the only formulation for subspace mechanics, but as you may have gathered, we are pursuing it here. And the first thing we're going to do is review some of the nomenclature here. So if we integrate over our phase space, this is typically our phase space here, and let's just integrate our distribution over the phase space. So this is going to be a integral over all velocity space and an integral over all momentum space for a total of 6 integrals, all from minus infinity to infinity of our distribution. And this is over dvx, dvy, dvz, and d omega x, d omega y, d omega z. And this, of course, is our density of gyrons at a given location and time. So we've added up all the gyrons of all velocities and all angular momenta, all spins. And we write this as this is the 0th moment. And the idea here is that we build moments of our distribution function to demonstrate real fields that we observe in real space-time. And before we go into the time evolution of our fluid, let's do a couple other moments. For example, we have this moment of putting the velocity in, integrating that. And this is our bulk velocity, often written as u. And sort of like a wind speed, so we've integrated the velocity. Oh, and there's a factor of the density here as well, so this is a flux of our gyrons. And this enables us to write the velocity of an individual gyron, v, as a sum of the bulk velocity and a peculiar velocity, which is useful. And again, this is all ancient fluid mechanics here. There's nothing new going on. Higher order moments are possible as well. For example, we might want to consider a component in, make a tensor field by integrating, multiplying by these components of the velocity. And this will give us the bulk flow plus a term which is a pressure tensor. And the pressure tensor here, as we defined it, is the integral of our peculiar velocities. Of course, we have the integral, we have the average peculiar velocity is going to be 0 by definition, because the average velocity is just this, u, the bulk velocity. Now we also have, because we've included a spin, we have other first order moments. This is a second order moment, this is a first order moment. This is a second order moment. And we have another first order moment right here. Sometimes we call this omega bar. Average bulk spin if you will. And of course we have a density. Whenever we take this integral over our distribution function, we're going to have a density. And this is the preliminary set of variables and moments that we can work with. So let's go ahead and write our time evolution equation, which comes from Liouville. And assuming a smooth distribution, we have that the partial derivative with respect to time plus the other partials to form the complete derivative. And I'm using the subscript to indicate the component here. I'm not trying to indicate that this is a contravariant or covariant vector. I know a lot of general relativity texts from Misner, Thorne, and Wheeler, and Schrodinger's little text all emphasize keeping track of whether how your vectors transform covariantly or contravariantly. So for now, we're not going to bother with that formalism. We just keep these as components, which makes it a little simpler for this presentation. Now we assume that this acceleration term is 0, this torque term is 0, and we have that this term here is actually just the velocity again. So this simplifies to a nice neat form. And again, we're saying that this is equal to 0 because we're assuming that there's no collisions, which is of course a bad assumption, but it's going to give us the main characteristics. Typically you'd have a collision term here on the right hand side, but we're going to use this as our master equation for now. And from this we can multiply it and integrate. Well, let's first integrate it through the 0th order moment. If we just integrate this equation directly over all phase space, so I'm just going to write with a single integral even rather than writing all 6 of them. D to the 6th. Let's call the phase space S. And let's go ahead and write these integrals in terms of our quantities. Because we have a nice smooth integral, we can go ahead and reverse the order of these operators, giving us this. And because, let's do an aside over here, we have that this term here is actually equal to the derivative with respect to xi of f times vi. And this is by the chain rule because you do have to subtract the by the chain rule this term, but this term is 0. These are independent variables. And so we can write this guy here as the integral of d by dxi of f vi d to the 6s. Now this term on the left we see is just the nothing other than the density that we described up here. This term here. So this is dn dt. And again, switching up the order of the variable of the operators here, we have d by dxi, the integral of f vi d to the 6s. And this is nothing other than our first order moment of the velocity, average velocity. So we have d by dxi of what we're calling n times u. This is going to be the first equation that we've pulled out of our boxed master equation here. And this is nothing other than the continuity equation, which you are probably more familiar with, written as a divergence. My apologies, I'm mixing my notation here. Sorry about that. Of n times ui, and n times ui is a flux. And so this is our continuity equation. And we're going to go ahead and take some higher moments and repeat the same procedure. So the first thing we're going to do is multiply our master equation by velocity. So I'm just going to go ahead and rewrite this. We have the time derivative of f with respect to t plus, we're multiplying now by vj across the whole equation. And we're going to integrate this now. So as we do this integral, we're going to have some of the same procedures we had before, where on the leftmost term here, if we integrate this over all phase space, we're going to have d by dt of n ui uj. Let's leave it as j because that's what I chose there. And then this term is a d by dxi of our n ui uj, and we're going to have a term with the peculiar velocities. And this is our momentum transport equation. If we had mass in here, we'd be calling it a momentum transport equation. And we can also make a similar equation for multiplying our master equation by omega instead of v to get another first order transport equation. Let's go ahead and do that. So we're going to wind up with the time derivative of n times the bulk spin, leaving this as a component here, plus spatial derivative and finally the peculiar component. Am I getting my indices confused here? We want j in the end, so we're going to sum over the i's. That's right. Master equation, we took the derivative with respect to xi. So there's a vi, sum over. And we can go ahead and add higher order terms as well. So we're going to go ahead and add a omega I vj to our original equation. Let's write this out before we do the integration. write out the master equation, multiply it with our term omega I Vj df dt plus omega I Vj, and now we must sum over another index, so it's going to be k. Now we're going to integrate over this. And this will give us, in the same manner as our previous moments, now I'm going to write this as, excuse me, I'm going to write this as the spin pressure tensor, leaving the n inside it, as that, like that. And then we have d by dxk now of omega I Vj Vk. And so this is a second order transport equation. And what we can do with this term is we can simplify it, break it into two parts. This large term here, we're going to call it the bulk component times the pressure tension, the peculiar pronoun of the velocities, and then a term which is the peculiar components of each. And because we're going to assume that this is isotropic, then we can safely ignore this term. So at this point, what we can do is notice that we have this term here, which is similar to this term here. So what we're going to do is take a time derivative of this first equation and a spatial derivative of this second equation. So let's do that explicitly. We have a time derivative of the first one, so it's now a second time derivative, d by dt of d by dxj, or n ui omega j here. And then from our second order term here, we're going to take a xj derivative. So we're going to have a d by dt, d by dxj of our n ui bulk omega j Oops. Very sorry about that. And now this is the second spatial derivative, dxj, d by dxk. So now if we subtract these two equations, noticing that we have the same term here, we see that we have the second time derivative of our bulk velocity. And now this is a minus, excuse me, d by dxj, d by dxk. And this is a wave equation. As we can tell, if we assume that we have a diagonal pressure tensor. So we're going to assume that this is now the average peculiar speed squared. C is the average difference in speed of a particle from the bulk velocity. And this is enables us to write this in a simpler way, because you can, well, let's do it out. We have second derivative of time of our bulk spin and c squared delta ik. And now I'm keeping this as a vector here. My apologies for mixing these notations. And this is the Laplacian c squared, of course. And so we have a wave moving at the speed c, which can form of a bulk spin of our medium. So if we take that our bulk spin omega bar sub I, the ith component of it is going to be proportional to the magnetic field we observe in real space. Then we see that we have these magnetic field waves which pass through the fluid. And note that they don't depend on a changing end. You could have the density the same everywhere, the gyron density the same everywhere, and you'll still have this. If it's constant, it just drops out. We just have a wave in bulk spin, and so even in a incompressible subspace fluid, you still have these spin waves. And also note that when you're in an area of enhanced, when there's extra energy here, you're going to have this energy is going to, when you have less of it, that energy will be in the pressure. So you're going to have a gradient in pressure as well, so which will be perpendicular. And so this is the sort of concept of how we explain light in a quasi-fluid subspace mechanics. And of course, we can take higher order pressure tensions. We're going to look in more detail. We drop the collision term everywhere here and assumed isotropy. So this is just a simple derivation of the equations that govern light from a fluid subspace formalism. And so we'll tune in next week and we'll get into some more details. Thank you.